Now we're going to look into integration by parts, which is essentially trying to turn around the product rule for derivatives. In this particular video, we're going to focus on the case of indefinite integrals. Of course, we know that via the fundamental theorem of calculus, we can get a counterpart for definite integrals. So what can we obtain from the product rule for derivatives in terms of integrals? Recall that the product rule states that to differentiate a product of two factors, we differentiate the first factor multiplied by the second unchanged, and then add the product of the derivative of the second factor with the first factor unchanged. So let's say I want to isolate one of the mixed product on the right hand side. So I get f of x times g prime of x equal the derivative of the product minus f prime g. If I integrate both sides, I get the integral of f times g prime is equal to the integral of the derivative of the product f times g minus the integral of f prime times g. Now this term can be simplified because here we are looking at an antiderivative of the derivative of f times g. So of course f times g is one antiderivative of its derivative. So we can replace that term by f times g and we obtain what we will call integration by part formula, which is that the integral of f times g prime is equal to f times g minus the integral of f prime g. Now we are often going to rewrite that formally slightly differently in a form that is a little bit easier to remember. In this formula we're going to call f of x u, and du is f prime dx, and v will be g of x, and dv g prime dx. And with this formalism, the integral on the left hand side becomes u dv. Then we have f times g, which is a product uv, and the integral of f prime g becomes integral of v du. And this is what we will call the integration by parts formula. So let's see on some examples how this applies. Here is our formula, and here is an integral we want to calculate. Here there is certainly no hope in terms of using substitution, for instance. So we can, say, try integration by parts. To do that, we have to pick which one of the two functions x and sin x are going to be v and u. Well, more explicitly, u and dv. So one of these two terms is going to be u, the other one dv. U is going to be differentiated, dv is going to be integrated. So we need to pick in such a way that we get something simpler. So if I differentiate x, I get 1. So I simplify. When I integrate x, I get x squared over 2. I get it more complicated. On the other hand, for sin x, whether I differentiate or integrate, I get essentially the same thing, a cosine. So I'm going to pick for u x, because this is the term I'm going to differentiate, and I want to simplify the expression, and for dv, sin x dx. I need to calculate du and v. So if u is x, du is dx. If dv is sin x dx and v is an antiderivative of sin x, negative cosine x. And then, this is what I obtain applying the formula, because uv is a product of x times negative cosine x, so it's negative x cosine x. And the integral of v du is the integral of negative cosine x dx. So, I obtain negative x cosine x plus the integral of cosine x, which is sin x up to a constant. Let's look at a second example. A pretty similar one. We want to integrate x e to the negative x. Again, I have to pick what is going to be u, what is going to be dv. Again, the rule of thumb is the same. I'm trying to simplify. And so for x, to simplify, I should differentiate. Whereas for e to the negative x, I get the same complexity if I integrate or differentiate. So I'm going to integrate e to the negative x and differentiate x. So u is x, dv is e to the negative x dx. Then I have to calculate du and v. Du is dx, and v is an antiderivative of e to the negative x, which could be negative e to the negative x. Then we apply the formula. uv is a product of x by negative e to the negative x, so I get negative x e to the negative x, and v du is negative e to the negative x dx, so I get minus the integral of negative e to the negative x, in other words, plus integral of e to the negative x, and integral of e to the negative x is negative e to the negative x, so I obtain negative x e to the negative x minus e to the negative x up to a constant. Now let's look at another example. Let's say we want to integrate cosine x ln of sine x dx. Again, we need to pick what is going to be u, what is going to be dv. So cosine x, whether I differentiate or integrate, I would get the same complexity as sine. ln of sine x, well, I don't have much of a choice because I know how to differentiate ln of sine x, but we don't really know what to do to obtain an antiderivative of that. So if we're going to try to use integration by parts, then the only choice would be to take u equal ln of sine x because we know how to differentiate it. Now one remark, before we jump into integration by parts, you might say, wait a second, we can use substitution here. I can take u is sine x, and then cosine x dx is du, and I get integral of ln of u du. Well, yes, but then what are we to do with this integral of ln of u du? So because we don't know what to do with that one, I'm going to use integration by part directly on this without doing this substitution. So as I said, u has to be ln of sine x because I don't know how to integrate it. And therefore dv is going to be cosine x dx. As usual, I'm going to calculate du and v. Du is a derivative of ln of sine x. I have to use the chain rule. So I get 1 over sine x multiplied by the derivative of sine x. So in other words, I get cosine x over sine x dx. If dv is cosine x dx, v is an antiderivative, which is sine x. Then I plug things in. uv is sine x multiplied by ln of sine x. And integral of v du is the integral of sine x multiplied by cosine x over sine x dx. You see that I have sine x over sine x, that cancels out. So I end up with simply sine x ln of sine x minus the integral of cosine x. And the integral of cosine x is just sine x. So we obtain sine x ln of sine x minus sine x up to a constant. Now in the previous example, we ended up picking the natural log for the function to differentiate because we didn't know how to integrate it. Right? I pointed out that we could have used the substitution that would have led to this integral, integral of ln of u du. Can we calculate this integral? Well, we can use the same logic that we applied in the previous example. In other words, that sometimes if there is a function for which we know the derivative, then we can try to use integration by parts and differentiate that particular function. Even though integration by parts is usually something to integrate a product, certain kinds of products, and this particular integral doesn't really appear to be a product, you can always consider it as a product of a function by 1. So we know how to differentiate ln of x, so I'm going to take u is ln of x, and then dv is what remains, in other words, dx. Calculating du is just dx over x, and an antiderivative of dx is just x. Then uv is x ln of x, and v du is x times dx over x. The x simplifies out, and we end up with x ln of x minus the integral of dx, which just gives x. So we get x ln of x minus x up to a constant. Now this way of obtaining an antiderivative for certain functions for which we know the derivative is a standard trick. So In particular, the antiderivative of ln of x, you don't necessarily need to remember the result, the formula, that the antiderivative of ln of x is x ln of x minus x up to a constant. But you need to remember how to obtain it quickly, and this is just by parts. And once you decide to do it by parts, you have no choice. You differentiate ln of x because precisely you're looking for the antiderivative, so you cannot use the antiderivative. Now there are other functions where we can use the same trick. For instance, we can use the same trick to obtain an antiderivative of arc sine x. So we're going to use integration by parts where we differentiate arc sine x and therefore integrate dx. du is then dx over root of 1 minus x squared, and v is x. So uv is x arc sine x, and v du is x over root of 1 minus x squared dx. Now in this integral, we can now use substitution because we have a composite part. We have 1 minus x squared plugged inside the square root function, or more precisely 1 over square root. And at the top we have x dx, which is a constant multiple of the derivative of what's inside the square root, because the derivative of 1 minus x squared is negative 2x. So we use the substitution w is 1 minus x squared, which gives us dw is negative 2x dx, or if you wish, x dx is negative 1/2 dw. So in this integral I'm going to replace x dx by negative 1/2 dw and square root of 1 minus x squared by square root of u. So we obtain x arc sine x plus 1/2 integral of dw over root w. Well, 1 over 2 root w is the derivative of root w, in other words, an antiderivative of 1/2 an antiderivative of 1 over 2 square root of w is root of w. And w was 1 minus x squared. So we obtain x arc sine x plus root of 1 minus x squared up to a constant. A third example, where we can try to use the same trick of integration by parts to find an antiderivative, is arctangent x. Because we don't know an antiderivative, but we know the derivative, so we can try by parts differentiating arctangent x. So we take u is arctangent x, dv is dx, therefore du is the derivative, 1 over 1 plus x squared times dx, and v is x. uv is x arctangent x, and v du is x over 1 plus x squared dx. Now in this integral, we can use substitution, because what we have at the top, x, is a constant multiple of the derivative of the bottom, and 1 plus x squared has derivative 2x. So we use a substitution like that. W is 1 plus x squared, and so dw is 2x dx, or in other words, x dx is 1/2 dw. So we replace x dx by 1/2 dw, 1 plus x squared by w, and we obtain x arctangent x minus 1/2 integral of dw over w, whose antiderivative is natural log of absolute value of w. Because w was 1 plus x squared, it's in particular positive, and so we obtain x arctangent x minus 1/2 natural log of 1 plus x squared up to a constant. One last example that is of slightly different nature. We're trying to integrate t cubed e to the t. First we should see if there is an easy way to obtain this integral. We don't know the antiderivative right on top of our head, and there's no obvious substitution, so integration by parts is an option. First we need to pick what is going to be u, what is going to be dv. We use the same rule of thumb as usual, try to see what would be simplified. E to the t, whether we differentiate or integrate, we're going to still get e to the t, so the complexity is going to be the same. T cubed on the other hand, if we integrate we get t to the 4 over 4, if we differentiate we get 3t squared. It looks like we're better off by differentiating, so we're going to take for u t cubed, and for dv e to the t dt. Applying the integration by parts formula, we obtain uv, which is t cubed e to the t, minus integral of v du, That's e to the t times 3t squared dt, so we obtain minus 3 integral of t squared e to the t dt. So here the problem is that we changed the integral, alright, but in the previous cases, each time we used integration by parts, we transformed the integral into some function plus another integral, and that other integral was easy to calculate. But now we transformed it the same way, a function plus another integral, but it's still not clear what this integral is. We obtain integral of t squared to the t, and it looks pretty much as difficult as the previous one. Not quite though, because we started with integral of a polynomial of degree 3 times e to the t, and now we have an integral of a polynomial of degree 2 times e to the t. If we use integration by parts on that again, the same way, differentiating t squared, we should expect to get an integral of a polynomial of degree 1 times e to the t. And doing it again, getting just integral of e to the t. So this is exactly what we're going to do, iterate this process. So I'm going to iterate this process and use integration by parts for the integral of t squared e to the t. Differentiating t squared, integrating e to the t. Derivative of u is 2t dt, and antiderivative of e to the t is e to the t. So we get t cubed e to the t minus 3 times what we obtain using the integration by parts formula on this second integral, namely uv, that's t squared e to the t, minus v du, that's 2 integral of t e to the t dt. So that simplifies as e to the t multiplied by t cubed minus 3t squared plus 6 integral of t e to the t. Well, we're still not done, but as expected, we now have an integral of something of degree 1 times e to the t, so if we do it once more, we should get just a constant times e to the t. So we're going to again differentiate t, integrate e to the t. So we obtain dt for du and e to the t for v, and apply the integration by parts formula for this integral. So we have the first term that is unchanged, e to the t times t cubed minus 3t squared, plus 6 times what we obtain applying the integration by parts formula, namely uv is t to the t, integral of v du is just the integral of e to the t dt, but integral of e to the t is just e to the t, so we obtain 6t e to the t minus 6 e to the t, and factoring e to the t, we obtain e to the t multiplied by t cubed minus 3t squared plus 6t minus 6, all this up to a constant. Now turn to the next video to see how we apply this integration by parts formula in the case of definite integrals.